Hello, and welcome to your first linear regression lecture. Now, because you've had a stats prerequisite, I'm assuming you know a little bit about what linear regression is. But as a review, linear regression is when we take a bunch of different inputs, and these can be continuous or categorical variables, and we use them in order to predict a continuous output. The way we do this is with a straight line, or if there's multiple predictors, technically a flat plane. And linear regression comes with a bunch of different assumptions, some that are more important than others. The first assumption is literally in the name, the assumption of linearity. The assumption of linearity says that the relationship between each of our inputs and our output, the thing that we're predicting, is roughly linear, meaning it is well described by a straight line. In this plot here, you see a violation of this assumption. Here, the data has a very clearly non-linear pattern, meaning we violated this assumption that the relationship is linear. Another assumption of linear regression is quite hard to pronounce. It's homoscedasticity. The homo means same, and basically this assumption is saying that the variance of the errors that our model makes is the same throughout the entire model. When we look at this plot, we can see that this is a violation of homoscedasticity. As we look across the x-axis, we see that there are some regions where the error is very small and other regions where the error is really huge. Thus, we have violated the assumption of homoscedasticity. This is actually heteroscedasticity. This cone shape is a really common way to see heteroscedasticity, but it's not the only way. What we're looking for is some regions with really low error variance and some regions with very high error variance. Last, we have the assumption of normality. Now, this assumption doesn't really matter as much when we're in a predictive context like we are when we're doing machine learning. The assumption of normality more affects things like p-values and confidence intervals that you use when you're doing inference. However, technically we still have this assumption even though we didn't really care about it. The assumption of normality says the errors around our regression line are roughly normally distributed. This means that for a particular value of our predictor, the errors should be roughly normally distributed. That means that a lot of the errors should be relatively close to the line and less errors as you move outward. Here you can see a violation of the assumption of normality because our errors are pretty skewed. You can see that there's a lot of errors on this side and not as many on this side. Thus, we violated the assumption of normality. I just want to point out really quickly that the assumption of normality applies to the errors in the model, not the actual data. This assumption that our errors have a distribution is why you might often see this notation, where it says the expected value of y, given that we know the values of x, equals our regression equation. All this is saying is that if we know the predictor values, which we do because they're the inputs to our model, the expected value, or usually like the average value, is going to be given by this regression equation. We're not saying every single data point that has that value of x is going to have our exact predicted value, but the expected value of that distribution is the value predicted by our model. One really nice thing about linear regression is that it's super interpretable, which means that we can tell exactly how the model is making its prediction. The way we do that is with the different parameters of the model. In the case of a linear regression, we often have an intercept parameter as well as different slopes, which we call coefficients. These coefficients tell us how the predicted value changes when we change the different inputs of our model. For instance, in this really simple example, we're using shoe size to predict the number of cats that someone has. According to our slope, which is 1/2, every time we increase our shoe size by 1, our number of predicted cats goes up by 1/2. The intercept parameter tells you what the expected value is when all of our predictors are 0. So if somehow someone had a shoe size of 0, the intercept would tell us the predicted number of cats. Let's look at another simple example that predicts the weight of a person by their height. Here we can see we've used a straight line to model that relationship. The parameters of our model give us information about that relationship. For instance, the intercept says that if somehow someone was 0 centimeters, we would expect their weight in pounds to be -82. The coefficient for height tells us that as height increases by 1 centimeter, the predicted weight is going to go up by 0.97 pounds. And again, even though the output of the model in a linear regression has to be continuous, the predictors don't. We can also add categorical variables like the diet of someone, whether they're a meat eater or a vegetarian. Here, for the coefficient of diet, this tells us that if someone is a vegetarian, our predicted weight for them goes down by 7.6 pounds. And we're not limited to just a couple of predictors. In a linear regression, we can have multiple inputs to the model. For instance, here, I've also added age. In general, the interpretation of our coefficients is that a 1 unit increase, whether that's a centimeter or a year, causes our predicted value to either increase or decrease by the amount of the coefficient. So, for instance, for height, a 1 centimeter increase in height causes our predicted value to increase by 0.89. For age, a 1 year increase in age causes our predicted value to decrease by 0.12. Now, for categorical variables, it's a little tricky because in a category, an increase of 1 unit is going from one category, the one marked 0, to another category, the one marked 1. So for instance, here, vegetarian is indicated by a 1, meat eater by a 0. This means a 1 unit increase is when we go from being a meat eater to being a vegetarian. So here the interpretation would be being a vegetarian causes our predicted value to decrease by 8.2 pounds. Now, these interpretations are interesting, but often what we want to do is compare the relative magnitude of our different effects. For instance, does height or age have a bigger impact on your weight? Well, we can look at the coefficients and see which one is bigger in magnitude, but it's really hard to compare because how do we compare a 1 year increase to a 1 centimeter increase? Let's talk about a solution to this. We're going to take a quick detour to talk about z-squaring. To do that, what I want to do is talk about who is the GOAT. We're going to talk about 2 sports players, James Harden and Pete Alonso. Now, James Harden, at least in 2018, where this data is from, threw a ton of successful three-pointers, 378 of them, in fact, while Pete Alonso, a baseball player, made 53 home runs. Now, I want to know which one is the GOAT, but how do you compare a three-pointer and a home run? It's not really that clear. Now, one thing I could do is compare these players to their peers. We could see how much better is Pete Alonso compared to his peers, compared to James Harden above his peers. Here we have graphs that look exactly at that. Here we have James Harden represented by this line, and we can see he is head and shoulders above his peers. But so is Pete Alonso. He's quite a bit better than all of his peers. So what do? Well, maybe we could z-score. A z-score has 2 really important operations that it does. The first thing that it does is it takes each of our individual values and it subtracts the mean. That little bar above our x variable just means like the mean for all of our different x's. By mean centering our variable, we get this really nice property where positive values are going to be values that are above the mean, and negative values are values that were below the mean. This helps us compare. So now, for instance, we could see if both James Harden and Pete Alonso have positive values. But we're still comparing three-pointers to home runs. So z-scoring does a second additional step. It divides by the standard deviation of our variable. This puts our z-score in units of standard deviations. So a z-score of 1 means you're 1 standard deviation above the mean. A z-score of -2 means you're 2 standard deviations below the mean. This allows our 2 scores, even though they're not perfectly the same, to at least be on a more comparable scale. Here we see a graph of the z-scored home runs and three-pointers for our 2 players. This informs us that James Harden actually has a much higher z-score than Pete Alonso, so he must be the GOAT. Again, to review, z-scoring does 2 things. it mean centers by subtracting the mean, and it divides by the standard deviation. This gives us a score that's easier to compare, even when the original variables weren't very comparable, like 3-pointers and home runs. So what does that have to do with linear regression? Well, when we have different predictor variables that have very different scales, like years and centimeters, we might want to actually z-score those variables before putting them into our model so that we can actually compare them when we look at our coefficients. Here we have the same exact model, except we z-scored our continuous variables. We don't want to z-score categories because what does it really mean to have the mean or standard deviation of a category? Now we can actually compare height and age, even though years and centimeters are quite different, because now both are z-scored. This changes the interpretation of our coefficients a little bit though. Now, when we look at a 1 unit increase in our variables, we're actually talking about a 1 unit increase in a z-score, for instance, going from 0 to 1 or 1 to 2. Because of the way a z-score works, this is now a 1 standard deviation increase in our variable. So, for example, for height, we would say that a 1 standard deviation increase in height causes our predicted value to increase by 13.4 pounds. Similarly, for age, we would say that a 1 standard deviation increase in age causes our predicted value to decrease by 2.5 pounds. Now that both of these are z-scored, we can more accurately compare their effects. For instance, here we would say height plays a much larger role in predicting weight than age does. Now, for the purposes of our class, the main reason to z-score our predictors is to help with understanding and comparison of our different variables. However, it also helps with model convergence. Now, for simple models like the ones we learn in this class, this isn't that big of a deal, but it's something to keep in mind, especially if you get into neural networks later on. Z-scoring, putting all of our variables on similar scales, can actually help the model fit a lot better and a lot faster. So now that we know what linear regression does, let's talk a little bit about actually building or fitting our model. Now, when we have data like this simple case where we just have one predictor on the x-axis and our outcome on the y-axis, there are a bunch of different straight lines that look like they might accurately describe the relationship between our data points. So how do we choose just one? Well, one thing we might want to do is minimize the errors that our model makes. Another word for an error is a residual, but both of these are just the difference between the value that our model predicts and the actual value of our data point. We might want to choose a line that minimizes the sum of these errors. In other words, a line that is as close as possible to all of our data points. For mathematical reasons, we usually take these errors and square them before adding them all up. This gives us the sum of squared errors. We're taking our errors, squaring them, and summing them. We also might look at something called a mean squared error, which is just the sum of squared errors divided by the number of points. Basically, it tells us the average squared distance between our model's guess and the actual value. One really important thing to note is that when we square our errors before adding them up, we're giving large errors a huge influence in our model, because when you take a large number and you square it, it gets even bigger. So while intuitively that's how we want to choose our model, let's go ahead and talk about how we actually do it. The first method we're going to talk about for linear regression is called least squares, and mathematically it basically follows the intuition that we just talked about. In order to fit our linear regression line, we're going to assume a super simple model with just an intercept and one coefficient. In order to choose the best line, we have to choose an intercept and a coefficient that minimize the sum of squared errors. This is just a formula for the sum of squared errors. This little hat on the y means our predicted value for that point. First, let's replace that y hat, our predicted value, with the formula we use to make that prediction, which is here, the slope plus the intercept times our input. Now we have a full formula for how to calculate our sum of squares specifically for this regression. Now, I'm not going to make you do any of this by hand. I just want you to understand a little bit about what is happening here. If you've taken a calculus or a differential equations class, this might look really familiar. What we're going to do in order to find both our intercept and our coefficient that minimize the sum of squares is we're going to take this formula and we're going to find the partial derivatives and set them equal to 0. Remember, when it comes to derivatives, the derivative is 0 usually at the minima and maxima of a function. So if we want to minimize our sum of squared errors, we can find the derivatives of our function and set them equal to 0. That should be where the minima occur. Now, again, you don't have to calculate this by hand, you can just trust me, but here are the partial derivatives of our functions with respect to each of our individual variables. This variable says the partial derivative with respect to the intercept. This says the partial derivative with respect to the coefficient. We then take both those derivatives and we set them equal to 0. This allows us to solve for what the best values of the intercept and the slope will be. Again, not going to make you do the math by hand, but if you did, and you can check out the full proof at the link below, you can see that we can figure out exactly the value of our different parameters. For the intercept, the value is going to be the average outcome value minus the predicted coefficient times the average input value. For the coefficient, we can see that it's going to equal the covariance of our input and our output divided by the variance of our input. If you do a little bit of algebra, you can also show that this is equal to the correlation of our two variables times the ratio of their standard deviations. So that's least squares. We can take our sum of squared errors, which we'd like to minimize, take the partial derivatives, set them equal to 0, and solve, giving us the values for our intercept and our coefficient. Another more flexible way that we can find the values of our parameters is with maximum likelihood estimation. Now, this formula may look a little bit intimidating, but we'll break it down. Essentially, maximum likelihood estimation wants us to choose parameter values that make the data likely. To break down this equation, this part is basically saying the values that we're going to pick for our parameters, aka our slope and our coefficient, are parameter values of all possible parameter values that maximize, that's what this max is, the likelihood of the data when using these parameter values. Well, what does that mean? When we look at the likelihood of something, we're basically saying, given these specific parameter values, how likely is it that we would see our given value? For instance, here's a really simple problem. Here we have a line representing the value of 1.5. Now, we want to choose a normal distribution that maximizes the likelihood of this value. For the sake of simplicity, we're only going to consider 3 different distributions. First, a normal 0, 1, then a normal 0, 0.5, and finally a normal 1.5, 1. These numbers just represent the mean and the variance of our distributions. Now, when we talk about likelihood, we want to choose one of these 3 distributions that makes our value of 1.5 the most likely. We can tell the likelihood of a value by looking at the height of the distribution. For instance, here between our 3 distributions, our blue distribution here has the highest likelihood of seeing the value of 1.5. In fact, seeing a 1.5 is pretty unlikely in this middle gray distribution and incredibly unlikely in this tall yellow one. So in order to maximize the likelihood of our data, we are going to choose this blue distribution. So we're going to pick the parameters 1.5, 1 as our normal distribution parameters to maximize the likelihood of our data 1.5. And that's essentially what we're going to do with maximum likelihood estimation for our linear regression. Now, the math of maximum likelihood estimation is a little bit complicated, so we're not going to do it by hand, although I've linked a proof below if you would like to do that yourself. What I do want you to know is that for linear regression with our given assumptions, the maximum likelihood estimates for our parameters are actually the exact same as the least squares estimate. Our intercept is going to be the mean outcome value minus our predicted coefficient times the mean input value, and the coefficient is going to be the covariance of our input and our output divided by the variance of our input. Now that we know how we could choose the parameters of our model, in this case our slope and any coefficients, let's talk about how we can assess how well our model actually did. One way to assess our model is to use something we've already talked about, the mean squared error, where we take the difference between our actual values and our predicted values, square that difference, add them all together, and divide by n. This gives us the average squared distance between our actual values and our predicted values. One nice thing about the mean squared error is that it makes a really good loss function. Loss functions are important for a lot of our models. They're basically a metric, so a number, that tells us about the performance of our model, where smaller values of that metric indicate a better performing model. Mean squared error is a perfect loss function because it does exactly that. The mean squared error is a number that tells us how well our model performs, where a lower value means better performance. In fact, a mean squared error of 0 means we're making perfect prediction. But this isn't the only way we can measure the performance of our model. We could also use a mean absolute error. Mean absolute error looks pretty much the exact same as a mean squared error. The only difference is we don't square our errors before adding them up. We take the absolute value. Now, one advantage of this is that the units of our mean absolute error are a little more easy to understand. The mean absolute error tells you the average distance between our guess and the actual value. That's a little easier to understand than a squared distance, which is what the mean squared error tells you. But both the mean squared error and the mean absolute error have one tricky bit, and that's that the units of the mean squared error and mean absolute error are whatever the units are of what we're predicting. So if we're predicting years, it's years. If we're predicting centimeters, it's centimeters. That makes it hard to set a threshold for what a good mean squared or mean absolute error is, because for instance, if we're predicting the age of people, a 1 year difference is maybe a big deal. But if we're predicting someone's height, a 1 centimeter difference might be pretty good. And so in comes R squared. R squared is very similar to mean squared error, but it's unitless, meaning that for whatever we're predicting, it has the exact same scale. Most R squared values go between 0 and 1. This is a formula for calculating R squared, but I think it's a little easier to understand graphically, so let's talk about it that way. When we look at a set of data, we can see that there's variation in that data. One way to measure that variation is to look at the average value for the data and then calculate the distance of all of our data points to that average value. The more variable our data is, the farther away points are going to be on average from the mean. When we fit a linear regression model, our data is not usually perfectly on that regression line. In other words, the data varies around that regression line. R squared basically looks at that total variation in the data and subtracts the variation from our model. This basically gives us an idea of how much of the variance is explained by the model. Because we divide by the total variation, we basically get a proportion or a percent. R squared is often interpreted as the percent of variation explained by your model, where the higher the better. An R squared of 0 means we're explaining almost none of the variation, whereas an R squared of 1 means we're perfectly explaining all of the variation. If we have an R squared of 1, that means that we're making perfect prediction. Now, in machine learning, it's actually possible to get R squared values that are negative. So another way to interpret the R squared value is comparing it to just predicting the mean for every data point. For instance, if I were trying to predict all of your ages, one really good way I could do that if I knew nothing else about you is just to predict the mean age for everyone. I'll often be wrong, but I won't be that wrong. And so comparing an R squared is basically saying how much better is our model at predicting than just guessing the mean for every single data point. An R squared of 0 in that context means it's no better than predicting the mean. We might as well just do that. An R squared of 1 again means we're perfectly predicting every data point. In this context, an R squared that's negative means we're actually doing worse than just predicting the mean for every person. Last, we have the mean absolute percentage error. You might notice from the formula that this is very similar to the mean absolute error, but we're scaling those errors by the actual value. This helps us take into account the fact that if we have a value that's 1,000,000, a 1 unit error is a less big deal than if we had a value that was 0.2 and had a 1 unit error. So these are 4 common metrics that we use to assess how well our linear regression models are doing. We have the mean absolute percentage error, the R squared, and then the mean squared and mean absolute errors. Each of these tell us a slightly different story, but basically all of them measure how successful our model is at making predictions. All right, that's all I have for you. I will see you next time.